Something invisible just punched a hole through the galaxy. The universe is built from particles so strange they could unmake reality itself. We are going to hunt for them. By the end, you will understand the most exotic and dangerous forms of matter ever conceived, from cosmic bullets that could shatter worlds to a shadow substance that might be all around us. We will ask if a speck of this matter could devour a planet, and whether the greatest explosion in modern history was caused by a fragment of a dying star. What do you believe is the most stable substance in existence? To understand a cosmic bullet, you first need to know what it is made of. Everything you see, from the screen in front of you to the most distant star, is built from a surprisingly small set of fundamental particles. This is the standard model of particle physics, our best map of reality's smallest pieces. Think of it as the ultimate periodic table, but for things that cannot be divided any further. At the heart of ordinary matter are quarks. You will never hold a single quark in your hand. They are forever locked inside larger particles, bound by the strongest force in the universe. Quarks are the ultimate Lego bricks. Just as you can build a house or a spaceship from the same plastic blocks, different combinations of quarks build every atomic nucleus. The most familiar ones are the up and down quarks. A proton is 2 ups and 1 down. A neutron is 2 downs and 1 up. These 2 humble quarks are the bedrock of all the atoms in your body and in the world around you. But the quark family is stranger and larger. Physicists have discovered 6 distinct types, which they poetically call flavors. Alongside the reliable up and down, there are the charm and strange quarks and the immensely heavy top and bottom quarks. These heavier flavors are unstable and fleeting, created only in powerful particle accelerators or cosmic collisions. They decay almost instantly into their lighter, more stable cousins. This is where things get interesting, because the property that makes a strange quark strange is not just its name. It has a unique quantum signature. And to hold quarks together, the universe uses a force even stronger than the electric charge that binds atoms. It is called the strong nuclear force, and it comes with its own peculiar charge, whimsically named color charge. Quarks carry a color charge, red, green, or blue, and they must combine in ways that cancel out to white or colorless. This is why you never find a lonely quark. They are always in groups, bound together by a relentless exchange of particles called gluons, which act like an unbreakable rubber band. This entire system, with its flavors and colors, is the elegant, complex machinery that builds our stable, ordinary world. But what happens if you take this machinery and feed it a different ingredient? What if you replace the common up and down quarks with something far more exotic, like an abundance of those strange quarks, and then subject them to pressures beyond anything found on Earth? The rules of the game change entirely. The crushing heart of a dying star might hold the recipe for a new state of the universe. When a massive star exhausts its fuel, it collapses under its own weight and explodes in a supernova, an event so bright it can outshine an entire galaxy. What remains is a neutron star, an object of almost unimaginable density. Picture the entire mass of our sun, squeezed into a sphere the size of a city. The gravity on its surface is 100 billion times stronger than Earth's. Here, atoms as we know them cease to exist. The immense pressure overcomes the electromagnetic forces that keep electrons orbiting nuclei. Electrons are forced into protons, turning them into neutrons. The entire star becomes a single, gigantic atomic nucleus, a sea of neutrons packed together, touching. But could the pressure go even further? Some physicists asked a profound question. What happens when you squeeze a neutron star so hard that even the neutrons themselves break down? Remember, a neutron is not fundamental. It is made of 3 quarks held together by the strong force. Under the unimaginable pressure at the very core of the densest neutron stars, the boundaries between individual neutrons might dissolve. The entire core could become a vast, continuous soup of free quarks, a new phase of matter called quark matter. And if the conditions are just right, this soup might find its most stable recipe by including a generous portion of strange quarks alongside the usual up and down. This hypothetical, ultra-stable substance is called strange matter. The idea was given serious mathematical form in the 1980s by physicists like Edward Witten. He proposed that this strange quark matter might not just be a possibility. It could be the true, absolute ground state of matter itself. That is a staggering thought. It means that the iron in your blood, the silicon in rocks, the hydrogen in stars, all the familiar matter in the cosmos might be merely metastable. It exists in a higher energy state, like a ball resting on a ledge. Strange matter would be that ball at the very bottom of the valley. If this is true, then a chunk of strange matter, a strangelet, would be more stable than any diamond or any element on the periodic table. It would be the ultimate crystal, indestructible and permanent. And if such a thing formed in the cataclysmic collapse of a star's core, what could it become? The ultimate crystal might not be forged in a star's death, but in the universe's violent birth. In the first microsecond after the Big Bang, the cosmos was not filled with atoms or even protons. It was a seething, unimaginably hot soup of free quarks and gluons, a state physicists call the quark-gluon plasma. As the universe expanded and cooled, this plasma condensed into the particles we know today. But what if some of it clumped together and froze solid before that could happen? This is the hypothesis behind quark nuggets, also sometimes called nuclearites or strange matter nuggets. They are theorized to be stable, macroscopic lumps of strange quark matter that formed directly from that primordial plasma. Unlike a strangelet born in a stellar collapse, a quark nugget would be a relic, a fossil from the very first moments of everything. It would have been wandering the cosmos for over 13 billion years. If they exist, their properties defy common sense. A quark nugget is not a tiny particle. It could be the size of a grain of sand, a pebble, or even larger, but its density would be staggering. Remember, this is matter where the space between atomic nuclei has been completely eliminated. A single nugget the size of a sugar cube could contain the mass of a small mountain, weighing billions of tons. Because it is made of an equal mix of up, down, and strange quarks, it would be electrically neutral. It would not emit light or give off radiation. It would be a dark, ultra-dense, and nearly indestructible object. So how would such a thing interact with the world? Imagine one of these cosmic bullets, a pebble with the mass of Mount Everest, drifting silently through the interstellar void. It enters a solar system and heads directly for a planet like Earth. Because it is electrically neutral, it does not create the fiery streak of a meteor. The atmosphere offers almost no resistance to something this dense. It would punch through like a bullet through tissue paper. Upon impact with the ground, the story gets even stranger. A normal asteroid of similar mass would release cataclysmic energy, carving out a continent-sized crater. But a quark nugget is so small and dense that it might simply tunnel through the entire planet. It would bore a microscopic hole through rock and magma, displacing a tiny column of matter as it passes. The surrounding rock would flow back into the void behind it, leaving almost no trace on the surface. The planet would shudder from a sharp, deep seismic tremor with no obvious cause, a ghostly puncture wound. The nugget would exit the other side and continue on its endless journey, utterly unchanged. This raises an eerie possibility. Could such objects be passing through our planet and even through our bodies all the time, leaving only the faintest whisper of their passage? But a strangelet is a different kind of phantom, one with a far more unsettling reputation. If a quark nugget is a silent cosmic bullet, a strangelet is often portrayed as the ultimate cosmic virus. The core fear is not its impact but its touch. This hinges on a concept called strangelet conversion. The theory suggests that because strange quark matter might be the true ground state, a single speck of it could be more stable than the iron in the Earth's core. If such a strangelet came into contact with a normal atomic nucleus, it could, in principle, convert that nucleus into more strange matter. This newly converted material would then join the original strangelet, making it slightly larger. That larger strangelet could then convert another nucleus and another, initiating a runaway chain reaction. In this nightmare scenario, the entire planet could be transmuted, atom by atom, into a lifeless, growing lump of strange matter. It would be a quiet apocalypse, transforming everything from mountains to oceans into an inert, alien substance. This idea fueled genuine, though highly speculative, concern decades ago when powerful new particle accelerators were being built. The question was asked, could we accidentally create a strangelet in a high-energy collision? Could a laboratory experiment on Earth inadvertently trigger the end of the world? Scientists at facilities like the Large Hadron Collider have taken these questions seriously. Their answer, backed by extensive research and observation, is a resounding no. First, the conditions required to create stable strange matter are far more extreme than any collider can produce. We are talking about pressures and densities found only in collapsing stellar cores. Second, even if a microscopic strangelet was somehow created, it would be highly unstable and would decay almost instantly in our low-energy environment. It would have no chance to start a chain reaction. Third, and most convincingly, nature has been running its own particle collision experiments for billions of years. Cosmic rays, particles from deep space that strike our atmosphere with energies far beyond anything we can create in a lab, have been bombarding Earth and other cosmic bodies since their formation. If such collisions could produce stable, planet-eating strangelets, we would not be here to have the conversation. The universe would have long since turned itself into strange matter. Our continued existence is the strongest evidence that the strangelet doomsday is a physical impossibility. So while the idea is a fascinating thought experiment that highlights the exotic extremes of physics, it is firmly in the realm of theory, not a plausible threat. This shifts the question back to the cosmos. If we are not going to create one, and if they are not wiping out planets, how could we ever hope to find one? The silent passage of a quark nugget through our planet offers a clue to their detection, but it also points toward a far grander cosmic role. For decades, astronomers have faced a fundamental mystery. The way galaxies spin and clusters of galaxies move indicates there is far more gravitational pull than the visible stars and gas can account for. Something invisible, something that does not emit or reflect light, makes up about 85% of the matter in the universe. We call this shadow substance dark matter. The hunt for its identity is one of the greatest quests in modern science. Could quark nuggets, those ancient, dense relics from the Big Bang, be a part of the answer? If they formed in abundance in the early universe and have drifted through space ever since, their collective gravity could indeed contribute to that missing mass. They would be a form of dark matter known as macho, massive compact halo objects, lurking in the vast halos surrounding galaxies. Finding something that does not glow, however, requires ingenious methods. One possibility involves listening for their quiet song. As a quark nugget, which is electrically neutral overall, moves through the magnetic fields that permeate our galaxy, the intense forces inside it could induce a tiny, fluctuating electric current. This current might generate an extremely faint but distinctive pulse of radio waves. Sensitive radio telescopes could, in theory, pick up this whisper as a nugget passes by. Another method looks for scars from the deep past. Imagine a quark nugget striking an ancient deposit of mica, a mineral that forms in orderly layers. The nugget's incredible density would create a unique, microscopic damage trail as it passed through, a permanent fossil record of its journey that could persist for millions of years. Scientists have examined such minerals, searching for these telltale tracks. We can also listen for the echoes of impacts. When a quark nugget strikes a body like the Moon, which has no atmosphere to slow it down, the impact would not create a traditional crater. Instead, the energy would be released deep underground, producing a sharp, high-frequency seismic ping. Networks of seismometers placed on the Moon could one day listen for these distinct tremors, differentiating them from ordinary meteoroid strikes. Even experiments built for other purposes are joining the hunt. The Ice Cube Neutrino Observatory at the South Pole uses a cubic kilometer of deep Antarctic ice as a detector for neutrinos, ghostly particles from space. But its vast sensor array could also, in principle, notice the subtle flashes of light produced if a quark nugget interacted with the ice, leaving a signature unlike any other particle. Each of these methods is a long shot, a search for a needle in a cosmic haystack where we are not entirely sure the needle exists. Yet the pursuit continues because the prize is so profound. Finding a quark nugget would not just be the discovery of a new object. It would be a direct message from the universe's first moments and a key to unlocking the nature of the dark matter that shapes the cosmos. But the true danger of a strange matter object may not lie in its touch, but in its speed. The most terrifying form this exotic substance could take is as a relativistic cosmic bullet. Picture not a drifting pebble, but a microscopic speck of strange matter accelerated to a significant fraction of the speed of light. Its power would come not from conversion, but from pure, staggering kinetic energy. The universe possesses natural accelerators far beyond anything we could build. Consider the environment around a neutron star. These stellar corpses often possess magnetic fields trillions of times stronger than Earth. A quark nugget passing too close could be caught in this invisible, ferocious grip and slingshotted away at incredible velocity. Even more powerful are the shock waves from supernova explosions, titanic blasts that can hurl material across galaxies. Or imagine the ultimate cosmic slingshot, the swirling, violent space around a supermassive black hole. Any object surviving a close pass could be flung out like a stone from a catapult, reaching relativistic speeds. Now consider the energy such a tiny object would carry. A single grain of sand, if moving at 99.9% the speed of light, would strike with the force of a multi-megaton nuclear bomb. But a quark nugget is not ordinary sand. That same speck with the mass of a mountain would concentrate that apocalyptic energy into an impact point smaller than an atom. The result is almost beyond description. It would not create a traditional explosion. Upon striking a planet's atmosphere, it would behave more like a particle beam than a meteor. It would deposit its immense energy in a narrow, incredibly hot column, drilling into the crust and triggering a shock wave that could devastate a continent. The geological record of Earth holds scars of past cataclysms, events that caused mass extinctions. While the leading culprit for the dinosaurs' demise is a large asteroid, some have looked at other, more mysterious events in our planet's history and wondered if a different kind of projectile could be responsible. Could a relativistic strange matter bullet, leaving no crater and little trace of its own composition, explain a sudden, global catastrophe with an unidentified cause? The idea remains firmly in the realm of theoretical astrophysics, a dark what-if scenario that stretches our understanding of both matter and cosmic violence. It forces us to confront a simple, haunting question. What else is silently flying through the darkness, carrying the potential for creation or annihilation in its heart? The Siberian wilderness of 1908 holds a secret written in fallen trees. On a June morning, a blinding fireball streaked across the sky, followed by a shockwave that knocked people off their feet hundreds of kilometers away. When expeditions finally reached the remote Tunguska region, they found a scene of surreal devastation. Over 2,000 square kilometers of ancient forest had been flattened, the trees pointing radially outward from a central point, as if a giant hand had pressed them down. Yet at the epicenter, the trees remained standing, stripped and scorched. Most puzzling of all, there was no crater. No fragments of iron or rock were ever recovered. The traditional explanation points to a small asteroid or comet exploding high in the atmosphere, its energy dissipating as a massive airburst. This fits the evidence well, but the complete lack of any extraterrestrial material has kept the door open for other possibilities. Could this have been a strike from something far more exotic? Some physicists have revisited the data with a radical hypothesis. What if the Tunguska object was not an icy comet or a stony asteroid, but a relativistic quark nugget? Consider its proposed properties. A nugget of strange matter would be incredibly dense and small, perhaps just a few meters across or even less. Traveling at a significant fraction of light speed, it would enter the atmosphere not as a lump of rock burning up, but as a hypervelocity projectile. Its immense density means the atmosphere offers little resistance. It would not dramatically slow down or fragment like a normal body. Instead, it would punch straight through, transferring its colossal kinetic energy directly into the air along its path. This could create a superheated plasma channel, a cylinder of unimaginable temperature and pressure that expands violently, generating the exact kind of powerful shockwave and thermal pulse that flatten the forest. The lack of a crater is explained because the object, if it survived, would have tunneled through the atmosphere and continued into space or deep into the Earth, leaving no traditional impact site. The absence of debris is even more telling. A quark nugget is not a collection of minerals, it is a single, ultra-dense entity. If it did not completely vaporize upon interaction, there would be no rocky fragments to find, only traces of its energy deposition. This idea turns the Tunguska event from a tragic accident of celestial mechanics into a potential encounter with a relic from the dawn of time, a microscopic cosmic bullet that grazed our world. While the asteroid hypothesis remains the most scientifically supported, the quark nugget scenario offers a fascinating, haunting alternative. It challenges us to look at the blank spaces in our understanding and ask what else could have left that signature on the sky. The Tunguska event stands as a powerful, solitary question mark, yet the sky is full of mysteries that do not fit the standard catalog. For over a century, scientists have detected cosmic rays, particles from space that bombard Earth with energies far exceeding anything our most powerful accelerators can produce. We have traced some to supernova or active black holes, but the very highest energy ones, the so-called ultra-high-energy cosmic rays, remain a profound puzzle. Their origin is unknown. Could a fraction of these be the final, fading signal of a relativistic quark nugget? When such an object streaks through the interstellar medium, the intense forces at its surface might strip away particles or generate bursts of radiation, creating a unique, ultra-high-energy fingerprint as it travels. We are essentially looking for the exhaust trail of a cosmic bullet. This search for strange signatures extends to other enigmatic flashes on Earth. Decades after Tunguska in 1930, a similar event shook a remote part of the Amazon rainforest near the Curacao River. Witnesses reported a brilliant fireball, thunderous noises, and tremors that lasted for hours. Later surveys suggested evidence of a possible airburst, but the inaccessibility of the region and the time elapsed left the event poorly documented and open to interpretation. Much more recently, in 2009, a brilliant flash was detected by satellites over the South Pacific. The energy release was consistent with a sizable meteoroid, but no debris or crater was ever found, and the exact location over open ocean made investigation impossible. These are not proof of anything exotic, but they are blank spaces on the map, events where the conventional explanation feels just slightly incomplete. Proving that any of these were caused by strange matter is a monumental challenge bordering on the philosophical. The evidence would be transient, vanishing almost as quickly as it appears. A quark nugget impact would not leave a field of meteorites to analyze. It might leave only a pattern of destruction, a specific seismic signature, or a peculiar flash of light with a certain color. To build a case, scientists would need to detect multiple such events and find a common, bizarre thread that defies all other explanations. It would require a paradigm shift, a willingness to interpret the data through a radically different lens. We would have to accept that the cosmos not only contains bullets of exotic matter, but that they are striking our world, leaving ghostly wounds that heal almost before we can see them. The hunt, then, is as much about preparing our minds as it is about building better detectors. We must learn to recognize the whisper of something truly alien in the cacophony of cosmic noise. And if we ever do, it will rewrite not just a chapter in a physics textbook, but our entire understanding of what is out there and what has been passing through our skies, unseen and unknown for all of human history. The silence of the cosmos is mirrored by the controlled chaos of our most powerful machines. If quark nuggets are relics of the Big Bang and strangelets are born in dying stars, could we ever witness such exotic matter firsthand? The answer lies not in telescopes, but in tunnels deep underground where we attempt to rewind time to the universe's first moments. Our tool is the particle collider, and our goal is to create, for a fleeting instant, a state of matter not seen for over 13 billion years. At facilities like the relativistic heavy ion collider in the United States and the Large Hadron Collider in Europe, scientists do not simply smash protons together. For these experiments, they use heavy nuclei like gold or lead and accelerate them to over 99.99% the speed of light before forcing them to collide head-on. The aim is to concentrate so much energy into such a tiny volume that the protons and neutrons inside the nuclei melt. For less than a billionth of a second, in a space smaller than an atomic nucleus, the quarks and gluons that normally lie locked inside are set free. This recreates the primordial quark-gluon plasma, the seething soup from which all normal matter later condensed. It is a fireball 10 times hotter than the core of the sun, and it exists for a time so short it defies human comprehension. Within this microscopic inferno, physicists hunt for clues. Could strange quarks, normally so rare and fleeting, become abundant enough in this hot, dense soup to briefly form a droplet of strange matter? The detectors surrounding the collision point are technological marvels, layers of sensors that act as ultra-high-speed cameras, capturing the debris of this tiny Big Bang. They look for unusual patterns among the thousands of particles that spray out, signatures that might indicate the transient formation of something exotic, like a strangelet containing an equal mix of up, down, and strange quarks. The results are fascinating but unambiguous. These experiments have successfully created the quark-gluon plasma, a monumental achievement. They have even observed hints of phenomena where strange quarks play a prominent role. However, no stable, long-lived strangelet has ever been detected. Any cluster of strange quarks that might momentarily form is immediately torn apart by the incredible energy of its surroundings, evaporating into a shower of ordinary particles before it can even be properly born. This leads to the crucial point of safety, a question that has been asked since these machines were first conceived. The fears of a runaway conversion, of a laboratory-made strangelet devouring the Earth, are rooted in a misunderstanding of scale and stability. The conditions inside these colliders, while extreme for us, are tame compared to the routine violence of the natural universe. Our atmosphere is constantly bombarded by cosmic rays, particles from deep space that collide with air molecules at energies far exceeding anything our most powerful colliders can produce. The Moon, Mars, and other celestial bodies with no protective atmosphere have been enduring such collisions for billions of years. If these natural, far more powerful events could create stable strangelets, the evidence would be everywhere in our solar system. It is not, furthermore, any exotic matter created in our colliders exists in an environment of incredibly high temperature and low density. the exact opposite of the crushing, cold pressure inside a neutron star required for stability. It is like trying to form a stable ice cube in the middle of a blazing furnace. The putative strangelet would not have a chance to grow. It would vaporize instantly, its constituents becoming part of the expanding cloud of ordinary particles. So, while we cannot yet create a stable piece of strange matter on Earth, the attempt itself is transformative. These experiments are not about manufacturing cosmic bullets. They are about learning the rules of the universe under conditions so extreme they reveal the fundamental forces that shaped everything. Each collision is a window into our own deepest past, a glimpse of the forge where the ordinary was born from the extraordinary. Stability in the universe is not always what it seems. Consider a simple pencil. The graphite in its core and the diamond on a ring are both made of the same fundamental ingredient, carbon atoms. Yet their structures are profoundly different. Graphite is soft and layered, while diamond is the hardest known natural material. Under the immense heat and pressure deep within the Earth, carbon atoms rearrange into that dense, crystalline diamond structure because under those conditions it is the most stable form. This reveals a deep truth about matter. What we consider normal and stable in our everyday environment might only be a temporary arrangement. The true ground state, the absolute lowest energy configuration matter can settle into, could be something entirely different elsewhere. This is the revolutionary idea at the heart of the strange matter hypothesis. It suggests that the most familiar building block of our world, the atomic nucleus, might not be the end of the story. For decades, physicists have known that iron 56 is the most stable nucleus in the periodic table. It has the highest binding energy per nucleon, meaning it takes the most energy to pull it apart. This is why stars fuse elements up to iron, and why anything heavier requires the cataclysmic energy of a supernova to create. Iron is the ash of stellar furnaces, the ultimate product of normal nuclear physics. But in the 1970s and 80s, physicists like A.R. Bodmer and later Edward Witten and H. Terazawa asked a daring question: what if you went deeper? What if you looked past the level of protons and neutrons down to the quarks themselves? Their calculations suggested a staggering possibility. A bulk form of matter composed of roughly equal numbers of up, down, and strange quarks, what we call strange quark matter, might have a lower energy state per baryon than even iron 56. A baryon is simply a particle like a proton or neutron, a building block of atomic nuclei. If this hypothesis is correct, it means that a chunk of this three-flavor quark soup is more stable, more tightly bound, and more permanent than the most perfect iron crystal. In this view, every atomic nucleus in the universe, from hydrogen to uranium, is in a metastable state. It is like a ball carefully balanced on a high shelf. It can sit there for billions of years, seemingly permanent, but the true ground state is the ball at the very bottom of the valley below. A speck of strange matter would be that ball at the bottom. This is not a minor tweak to physics. It is a complete inversion of our hierarchy of stability. It proposes that the true, ultimate form of matter is not the complex architecture of the periodic table, but a simpler, denser, more fundamental substance born directly from quark ingredients. This single, elegant idea is the theoretical engine that powers every speculation about stable quark nuggets drifting through space. It transforms them from curious anomalies into inevitable relics. If strange quark matter is the true ground state, then it should have formed when the universe was hot and dense enough for quarks to mingle freely, and any piece of it that survived would be virtually indestructible, a permanent fossil from creation itself. The search for it becomes a search for the universe's most basic and perfect substance. So what would this ultimate substance actually be like? Let us build a spec sheet for a single, stable strangelet. Its most defining property is density. We measure density in kilograms per cubic meter. Water is 1,000. The densest element on Earth, osmium, is around 22,000. The core of a neutron star, the densest known object in the universe, reaches about 10 to the power of 17. A stable strangelet would likely match that or even exceed it. This number is almost meaningless to our human senses, so let us translate it. A single cubic centimeter of this material, a piece the size of a sugar cube, would weigh not grams but about 100 million metric tons. That is the mass of a small mountain, compressed into a speck you could balance on your fingertip. This is not merely heavy. It represents a state of matter where the empty space inside atoms has been completely erased, where quarks are packed shoulder to shoulder in a continuous solid mass. Next, consider its electric charge. A strangelet is made of quarks which carry fractional charges. In a perfect, stable mix of up, down, and strange quarks, the total charge should theoretically sum to zero, making the object electrically neutral. However, in the messy real world of particle physics, achieving perfect balance is tricky. A real strangelet might have a slight excess of one type of quark, giving it a small positive charge. This charge would be incredibly weak, but it would have a profound consequence. It would attract a thin cloud of electrons from its surroundings, hovering around its surface like a faint, shimmering aura. This electron cloud is crucial. It acts as a barrier, preventing the strangelet's powerful, strong nuclear force from directly touching and converting normal atomic nuclei. Instead of a voracious cosmic virus, a real strangelet might be more like a perfectly smooth, inert marble, its dangerous interior shielded by this delicate electromagnetic veil. This brings us to the most subtle yet most decisive property, surface tension. In a water droplet, surface tension is what holds the sphere together against the pull of gravity. For a strangelet, surface tension is an internal, quantum mechanical force that acts on its very boundary. Think of it as the skin of the droplet, a membrane under immense pressure trying to keep the quark matter inside from leaking away. This surface tension creates a minimum size for stability, known as the critical baryon number. A baryon number is simply a count of the proton and neutron-like units in an object. If a droplet of strange matter forms with a baryon number below this critical threshold, its surface tension wins. The pressure to minimize its surface area is too great, and the droplet will simply evaporate, its quarks flying apart. It is unstable, like a soap bubble that pops the instant it forms. But if the droplet forms above that critical size, everything flips. The bulk of the material inside overwhelms the surface pressure. The droplet becomes energetically favorable, and it is stable forever. This critical size is the gatekeeper. Estimates vary wildly, but it could be anywhere from a few hundred to many millions of baryons. That might sound large, but on a human scale, it is still subatomic. A stable strangelet could be far smaller than a single atom, yet denser than a star. This single detail of surface tension and critical size is why the laboratory doomsday scenario is pure science fiction. In a particle collider, we are creating a hot, expanding fireball. Any fleeting cluster of strange quarks that might momentarily glimmer into existence would be tiny, far below the critical baryon number. It would be born into an environment of extreme heat and low density, the exact opposite of the cold, crushing pressure needed for stability. That hypothetical microdroplet would not have a chance to grow. Its own surface tension would tear it apart in a fraction of a nanosecond, long before it could interact with anything else. It evaporates into a spray of ordinary particles, leaving no trace and no threat. The universe's natural forges, collapsing stellar cores, and the primordial Big Bang are the only places with the energy, density, and time to potentially cook up a droplet large enough to be stable. Our most powerful machines are merely playing with sparks, trying to understand the blueprint of the furnace. The pencil balanced on the shelf is stable, but the slightest nudge sends it crashing down. The universe may operate on a similar, terrifying principle of latent instability. This brings us to one of the most chilling concepts in theoretical astrophysics and futurism, a thought experiment that weaponizes pure physics, the relativistic kill vehicle. In science fiction, it is a doomsday device. In reality, it is simply a natural object obeying the laws of motion taken to an extreme. It is the ultimate cosmic bullet, and its power lies not in exotic composition, but in raw, unadulterated speed. Imagine taking a single gram of anything, a tiny paperclip or a raindrop, now accelerated to 90% the speed of light. The energy contained in that humble gram becomes monstrous. The equation for kinetic energy is not linear, it is exponential as you approach light speed. That 1 gram moving at such a velocity would carry the explosive yield of a small nuclear weapon, roughly equivalent to the bomb dropped on Hiroshima. Now replace that gram of water or metal with a single gram of strange quark matter. Remember, a gram of this substance is not a speck of dust. Due to its insane density, it would be a sub-microscopic dot, smaller than a virus. Yet it would pack that same apocalyptic energy into a target area tinier than an atom. The result is not an explosion in the traditional sense, it is a particle beam of pure mass. Upon striking a planet, this relativistic kill vehicle would not be slowed by the atmosphere. It would punch through like a hypersonic needle, transferring its colossal energy directly into the ground in a cylindrical shockwave of superheated plasma. The effect would be a deep, penetrating thermal and seismic event, potentially devastating a region without leaving a classic crater. Its small size and neutral charge make it a nightmare to detect. There is no fiery meteor trail, no reflective surface for telescopes, no large radar signature. It could emerge from the darkness of interstellar space with virtually no warning, a silent, unstoppable projectile traveling at a significant fraction of light speed. Our current planetary defense systems, designed to track and deflect large, slow-moving asteroids years in advance, would be utterly useless against it. The impact would occur minutes, perhaps seconds, after any theoretical detection. This transforms the relativistic kill vehicle from a sci-fi trope into a serious framework for existential risk assessment. It forces us to ask a sobering question about our place in the cosmos. If such objects are naturally occurring, peppered throughout the galaxy by ancient stellar explosions or black hole jets, then Earth exists under a permanent, statistical threat of an instantaneous, inexplicable catastrophe. The geological record is incomplete. Could some past extinction event bear the subtle, strange signature of such an impact? Furthermore, the concept invites a darker, more philosophical line of thought. If a naturally occurring speck of matter can be a planet killer, then a technologically advanced civilization, capable of accelerating just a few kilograms of mass to such velocities, could wield the ultimate deterrent or the ultimate weapon. A relativistic kill vehicle requires no warhead, no exotic physics, just a powerful enough engine and a ruthless application of Newton's laws. A single such projectile, launched from a distant star system, could arrive with no possibility of interception and deliver continent-shattering force. This is not a prophecy, but a logical extension of known physics. It underscores a profound vulnerability. Our survival on this pale blue dot may depend not just on the stability of our climate or our politics, but on the quiet, empty paths between the stars and on what might or might not be traveling down them at impossible speeds. The laws of physics are the same for everyone, but intention leaves a signature. If stable, strange matter is the universe's ultimate building material, then any civilization mastering its creation would hold a key to unimaginable power. This leads us into the realm of astroengineering, the theoretical megascale manipulation of cosmic structures and matter itself. Imagine a culture not bound by planetary resources, one that could harvest the raw material of neutron star crusts or even catalyze the formation of strange matter in controlled stellar collapses. Their projects would dwarf anything we can conceive. A single quark nugget, given its phenomenal density, could serve as the perfect reaction mass for an interstellar ramjet, a tiny pellet containing the energy of a starship's entire fuel tank. An array of such nuggets, precisely guided, could become a relativistic defense system or a tool for planetary terraforming, delicately nudging asteroids or comets. Most intriguingly, strange matter's theorized stability makes it a candidate for a form of eternal data storage. Information encoded in the quantum states of its quarks could, in principle, survive for billions of years, outlasting stars and galaxies. This is where speculation turns into a cosmic detective story. If we were to ever recover a specimen of strange matter, how could we tell if it was a natural relic or an artificial artifact? We would need to become quantum archaeologists searching for fingerprints in the subatomic structure. A naturally formed quark nugget from the Big Bang would be a chaotic, albeit dense, frozen droplet. Its internal arrangement of quarks might follow a statistical pattern, a snapshot of a random, violent freeze. An artificially crafted one, however, might bear signs of precision. Could its surface be unnaturally smooth, minimizing energy in a way turbulence would not allow? Might its charge be perfectly neutral, a balance too exact for nature's messy processes? Or could there be a pattern embedded within a layered structure, a deliberate isotopic ratio, or even a quantum signature etched into the alignment of its constituent particles? Finding such an object would present humanity with a paradox more profound than the artifact itself. The very properties that make strange matter the perfect, permanent material also make it the ideal message in a bottle. It would be indestructible, enduring across cosmic epochs. It would be dense, carrying vast information in a tiny package. And it would be exotic, immediately standing out from the background of normal matter to any civilization advanced enough to recognize it. The discovery would force a fundamental question. Are we looking at a fossil of the universe's birth or a fossil of someone else's technology? The answer would rewrite not only physics, but our entire understanding of reality, time, and our lonely place within it. The power to shape the fundamental substance of reality carries a weight far heavier than any quark nugget. This is no longer abstract astrophysics, it is a mirror held up to our own nature. The moment we move from discovering strange matter to deliberately creating it, we cross a profound threshold. We would be playing with cosmic fire, and the first question we must ask ourselves is not can we, but should we. Every profound discovery in human history has presented this dual-use dilemma. The equations of nuclear physics gave us a glimpse into the heart of the sun, but they also gave us the atomic bomb. Our mastery of biology unlocks cures for disease, yet it also opens doors to engineered pathogens. The rise of artificial intelligence promises to solve humanity's grandest challenges, while simultaneously posing risks to our very autonomy and survival. The pattern is clear. Understanding the deepest laws of nature does not come with an instruction manual for wisdom. The knowledge of how to synthesize stable, strange matter would be the ultimate expression of this pattern. On one hand, it could represent a leap forward for civilization. Imagine a material with the density of a neutron star core, stable at room temperature. A fragment the size of a marble could contain the energy equivalent of all the fossil fuels on Earth, potentially unlocking clean, limitless power through controlled annihilation or as an unimaginably efficient battery. It could be the foundation for materials science beyond our dreams, enabling construction on stellar scales or creating shields against cosmic radiation for interstellar travel. The positive potential seems boundless, yet the same properties that make it a miracle material also make it a perfect weapon. A manufactured strangelet, even a microscopic one, reintroduces the conversion risk in a controlled industrial context. While natural strangelets are likely harmless, a lab-created one designed for stability could, in theory, be engineered without the protective electron cloud, turning it into the very catalyst of doomsday we once feared was impossible. More pragmatically, the ability to produce and accelerate even neutral strange matter nuggets creates the ultimate relativistic projectile. A civilization that can make this substance can also weaponize it, crafting silent, undetectable bullets that could cross interstellar distances to strike with the force of asteroids. This is the core of the ethical chasm. The knowledge itself is neutral, but the human hands that wield it are not. Our history is a chronicle of ingenuity shadowed by conflict. Would the discovery of stable strange matter synthesis unite humanity in a common, cautious project of stewardship? Or would it become the ultimate strategic resource, triggering a new, hyper-advanced arms race? The responsibility lies not with the quarks, but with us. As we probe deeper into the fabric of reality, we are not just uncovering secrets of the cosmos. We are uncovering latent powers within the universe that have slept since the Big Bang. With each layer of physics we peel back, we gain more control over our environment, but we also expose ourselves to greater potential for catastrophic misuse. This forces a philosophical reckoning. Is there a point at which some knowledge is too dangerous to pursue? Or is the imperative to understand our universe an unstoppable force, with the hope that our wisdom can evolve fast enough to manage the powers we unlock? There is no easy answer, only the solemn recognition that the journey to the center of a neutron star is also a journey into the center of the human condition. We are driven by curiosity, ambition, and hope, yet we are haunted by fear, rivalry, and our own capacity for destruction. The strangelet, in its perfect, dense silence, asks us which part of ourselves will write the next chapter. Deep within a neutron star's crushing heart, the greatest transformation of all may be quietly unfolding. The immense pressure might not just compress neutrons, it could be dissolving them entirely, triggering a stellar-scale metamorphosis. This is the theory of the strange star, a celestial object born from a neutron star that has crossed a fundamental threshold. Think of it as a cosmic alchemy where the entire core, and perhaps the whole star, undergoes a phase transition from neutron matter to strange quark matter. It would be a giant, city-sized droplet of the universe's most stable substance, a quark star cloaked in the guise of a neutron star. The differences, while subtle to a distant observer, would be written in the star's fundamental physics. A strange star would likely be even more compact than its neutron star counterpart. With neutrons broken apart into their constituent quarks, the matter can pack together more efficiently. Imagine squeezing a bag of oranges, then crushing those oranges into a smooth, dense paste. The paste occupies less space. A strange star of the same mass as a neutron star might be several kilometers smaller in radius, a tighter, denser sphere of pure quark matter. This has a direct consequence astronomers can hunt for: the mass-radius relationship. For normal neutron stars, there's a predictable curve, how heavy they can get versus how big they are. Strange stars would follow a different curve. If we could precisely measure both the mass and size of a dense stellar remnant, a deviation from the expected neutron star line could be the first hard evidence of this exotic transformation. The surface of such an object defies all earthly intuition. A neutron star has a solid crust of iron nuclei. A strange star has no such crust. Its surface would be a bare quark boundary, a razor-sharp edge of strong force material only a few femtometers thick. That's 1 quadrillionth of a meter. Above this boundary hovers a vanishingly thin atmosphere of electrons, held by the star's slight electric charge. This quark surface would be unimaginably smooth, possibly the smoothest solid in the universe, constrained by the intense gravitational field and the nature of the strong force itself. This unique surface also changes how the star cools. Neutron stars cool by emitting neutrinos from their dense interiors. A strange star's quark matter could allow different, more efficient pathways for neutrino production, meaning it might radiate its fierce birth heat away faster. By studying the X-ray glow of very old, cold stellar remnants, Astronomers might one day spot an object that has cooled too quickly to be a neutron star, a candidate that has quietly become something else entirely. Some of the most promising clues come from the precise clocks of the cosmos, pulsars. These are rapidly spinning neutron stars that beam radiation like a lighthouse. Their rotations are incredibly regular, but they occasionally experience a glitch, a sudden, tiny speed up in spin. For normal neutron stars, this is thought to be caused by sudden shifts in the solid crust or the superfluid interior. The interior of a strange star, however, is a different beast. It could be a single, continuous superfluid of quarks. A glitch in a strange star would have to be generated by a different mechanism, perhaps involving vortices in this quark superfluid. The pattern and timing of these glitches could carry a distinct signature, but the ultimate test may come from the ripples in spacetime itself. When two such ultra-dense objects spiral together and merge, they create a unique gravitational wave signal, a chirp that encodes their properties in its waveform. The tidal forces during the final moments before collision deform the stars. A strange star, being more compact and stiff, would deform less easily than a neutron star. This difference in squishiness would imprint itself on the gravitational wave signal detected by observatories like LIGO and Virgo. A future merger event might produce a chirp that simply doesn't match what our models predict for two neutron stars, pointing instead to a collision of quark matter spheres. Each of these methods is a search for a ghost in the data, a subtle anomaly that whispers that beneath the familiar label of neutron star, an entirely new state of the universe has been hiding in plain sight. A collision between two strange stars would be the ultimate cosmic forge. When these ultra-dense spheres of quark matter spiral together, their final moments would write a unique signature onto the fabric of spacetime itself. As they draw closer, immense tidal forces stretch and deform them. But a strange star is not just a ball of neutrons. Its interior is a single, continuous superfluid of quarks, making it incredibly stiff and compact. It would resist deformation differently than a neutron star. In the last milliseconds before they merge, this difference in squishiness would alter the frequency and shape of the gravitational waves they produce. Observatories like LIGO and Virgo are essentially listening for these ripples. The signal from two merging strange stars would be a distinct chirp in the data, a deviation from the expected waveform of a neutron star collision. It would be a whisper in the noise saying, the objects that just vanished were not what we thought they were. The aftermath of such a merger is where theory explodes into spectacular possibility. The cataclysm would be unimaginably violent, ejecting material at a significant fraction of the speed of light. In a neutron star merger, this ejected material is thought to be the source of heavy elements like gold and platinum. But in a strange star merger, the ejector could be something far more exotic, blobs of strange quark matter itself. These blobs, if they were above the critical size for stability, would cool almost instantly into permanent quark nuggets. They would be relativistic cosmic bullets forged in the most energetic event since the Big Bang, sprayed out into the galactic environment. This provides a potential answer to a deep question. If quark nuggets exist, where do they come from? The primordial universe is one source, but mergers of strange stars could be a factory, continuously producing and distributing this exotic material across the galaxy. Every such collision could seed its corner of space with indestructible fragments, some of which might eventually wander into a solar system like ours. This transforms the search from pure theory into a testable, observational science. Astronomers are not just waiting for a lucky strike, they are actively building the tools to listen for these events. Each new gravitational wave detection is a data point, a puzzle piece. The goal is to find a merger whose signal cannot be fully explained by our models of ordinary neutron stars. That anomalous chirp would be the first direct evidence that strange matter is not just an equation on a whiteboard, but a real substance shaping the most violent events in the cosmos. It would mean that the ultimate stable matter of the universe is being created right now in stellar cataclysms millions of light years away. The implications ripple outward. If mergers spray strange matter into the cosmos, then the galaxy might be filled with more of these relics than we ever guessed. They would be the shrapnel from ancient stellar collisions, the silent bullets we have been searching for all along. The next time LIGO detectors twitch, they might be recording the birth cry of a quark nugget and the death rattle of a star that was never a star at all. Our most powerful eyes are now trained on the deepest sky, searching for the faintest glimmers of the impossible. This is not a hunt for a single object, but for a pattern, a signature written in the language of light and particles across the cosmos. The tools are space telescopes, satellites, and observatories, each designed to listen to a different part of the universe's story. One key player has been the Fermi Gamma Ray Space Telescope, specifically its Large Area Telescope instrument. Fermi scans the sky for gamma rays, the most energetic form of light. Why would this matter for strange matter? If strange stars exist, their bare quark surfaces and thin atmospheres of electrons should produce a very specific kind of gamma-ray emission. As electrons interact with the star's powerful magnetic field, they can be accelerated to incredible speeds and emit gamma rays in a predictable pattern. Fermi has mapped thousands of gamma-ray sources, including many pulsars. By analyzing the precise energy spectrum of this light from certain dense stellar remnants, astronomers can look for deviations, for a gamma-ray fingerprint that matches the unique theoretical predictions for a strange star's atmosphere rather than a neutron star's crust. It is a painstaking process of elimination, searching for an anomaly in the data that other explanations cannot satisfy. Beyond the glow of distant stars, scientists are also looking for sudden, violent flashes much closer to home. The Moon, with no atmosphere and a seismically quiet surface, is a perfect natural laboratory. When an object strikes it, the impact creates a brief flash of light. Networks of telescopes on Earth constantly monitor the lunar dark side for these tiny flashes, typically from small meteoroids, but a quark nugget impact would be different. Its immense density and potential speed would generate a flash with a distinct color and duration brighter, hotter, and possibly shorter than a typical meteoroid hit of the same apparent size. Dedicated projects have sifted through years of lunar impact data, looking for outliers that match this exotic profile. Finding even one such event with the right characteristics would be a tantalizing clue, a potential direct detection of a cosmic bullet striking our nearest celestial neighbor. The search extends to particles that barely interact with anything at all, neutrinos. Next-generation neutrino observatories like the planned IceCube Gen 2 in Antarctica or KM3 NET in the Mediterranean Sea will have volumes several times larger than current detectors. Their increased sensitivity makes them capable of detecting not just astrophysical neutrinos, but potentially the subtle signals of exotic physics. A quark nugget moving through matter, like ice or seawater, might produce a faint directional burst of particles or light as it interacts. While the chance is slim, these vast detectors act as giant nets, and a confirmed signal would be revolutionary. It would mean catching the particle wake of a relic from the dawn of time. Looking to the future, the James Webb Space Telescope offers another path. While it cannot see quark matter directly, its unprecedented power to study the infrared universe provides critical constraints. By observing the cooling curves of very old, isolated stellar remnants in nearby galaxies, Webb can help determine how quickly these objects lose their heat. If astronomers find a population of remnants that have cooled inexplicably fast, it could point to an interior structure more efficient at emitting neutrinos, exactly what models predict for a strange star's quark core. Webb's data won't provide a smoking gun, but it will sharpen our theoretical models, ruling out possibilities and narrowing the field. This multi-pronged, decades-long effort paints a clear picture. The hunt for quark matter is a mature, active field of observational science. It is no longer just speculation. It is a coordinated search using gamma rays, optical flashes, neutrinos, and infrared light, each method cross-checking the others. Every null result, every non-detection is not a failure. It tightens the constraints, telling us where these objects cannot be and what they cannot be like, slowly closing the net around the possible truth. We are listening to the universe with every tool we have, waiting for it to whisper back in a language we are only just beginning to understand. The safety of our most ambitious experiments is not an afterthought, it is the very first page of the blueprint. When the Large Hadron Collider was being designed, a very specific, though highly speculative, question was formally raised. Could this machine create something that could destroy the Earth? Among the scenarios examined was the possibility of creating a stable, negatively charged strangelet that could initiate a catastrophic chain reaction. The concern was taken with the utmost seriousness. Independent safety review groups comprised of some of the world's leading particle and astrophysicists conducted exhaustive analyses. Their reports, like the LHC Safety Assessment Group's findings, were made public. The conclusion was unequivocal. The risk of the LHC producing any dangerous object, including a planet-consuming strangelet, was effectively zero. This was not a guess, but a conclusion grounded in multiple layers of hard scientific evidence. First, consider the natural experiment that has been running for billions of years. Cosmic rays with energies far exceeding those in the LHC constantly bombard celestial bodies like the Moon and Earth. If such collisions could produce stable strangelets, the Moon would have been converted long ago. Its continued existence is a powerful natural safety certificate. Second, the conditions inside a collider are profoundly different from those inside a neutron star. We create an incredibly hot, low-density fireball that expands and cools in a fraction of a nanosecond. This is the worst possible environment to create something that requires extreme cold and immense pressure to be stable. Any exotic cluster of quarks that momentarily forms is born into a furnace and evaporates instantly, but physicists did not stop with theoretical arguments. They went looking directly in the data. Every collision is a potential event, and detectors can search for the unique signatures a strangelet would leave as it decayed. After years of operation and trillions of collisions, no such signature has ever been found. From this absence, scientists can calculate something called a production cross-section limit. In simple terms, the cross-section is a measure of how likely a process is to happen. By seeing zero strangelets, experiments can say, strangelets with dangerous properties must be extraordinarily unlikely to produce if they can be produced at all. The LHC experiments have now ruled out the existence of stable strangelets over a vast range of possible masses, charges, and lifetimes. They have literally drawn a map of parameter space and declared, dangerous strangelets cannot exist here or here or here. This process is a powerful example of science at its best. A theoretical risk was identified. It was scrutinized with rigorous, peer-reviewed physics. It was tested directly by experiment, and it was conclusively laid to rest not by authority but by evidence. This proactive, transparent approach is how big science maintains public trust. It shows that the quest to understand the universe's deepest secrets is guided by a profound responsibility for the planet that enables the search. The equations of strange matter began in journals, but their true explosion happened in our stories. Long before the public worried about particle colliders, science fiction writers saw the narrative potential in a substance that could unmake reality. One of the earliest and most chilling explorations came in the 1991 novel The Killing Star by Charles Pellegrino and George Zebrowski. It presents a galaxy where relativistic kill vehicles are not a natural hazard, but a weapon of choice for an alien civilization practicing preemptive genocide. The novel's terrifying logic is that any species advanced enough to be detected is a potential future threat, and the safest solution is a silent, light-speed strike that offers no warning and permits no defense. This story took the dry physics of kinetic impact and wrapped it in a profound existential dread, asking what might truly await us in the silent cosmos. It moved the concept from the blackboard to the human psyche, framing the universe not as a welcoming frontier, but as a dark forest where every civilization hides. Hollywood soon followed, drawn to the visceral fear of a runaway conversion. While most blockbusters simplify the science for spectacle, they capture the core anxiety. The idea of a chain reaction that transforms everything it touches, a kind of cosmic grey goo scenario, taps into a deep, primal fear of contagion and annihilation. Video games, from popular franchises to indie titles, have used quark nuggets or strangelets as ultra-dense power sources or mysterious artifacts, often called neutronium or exotic matter. They become the ultimate MacGuffin, a material so valuable and dangerous it drives entire galactic wars. This translation from paper to pop culture is crucial. It takes concepts locked behind years of study and makes them feel immediate, giving audiences a visceral, emotional stake in questions of theoretical physics. We might not grasp the mathematics of the strong nuclear force, but we instantly understand the terror of a droplet that eats planets. A key bridge between these two worlds has been the public scientist. Figures like Michio Kaku, with his accessible explanations and willingness to engage with speculative futures, have played an enormous role. By discussing strangelets and relativistic kill vehicles in documentaries and books aimed at a general audience, they validated these ideas as worthy of serious thought, not just pulp fiction. This created a feedback loop. The sensational doomsday scenario, once introduced, sparks public curiosity and concern, which leads to more media coverage and more questions for scientists to address, as we saw with the Large Hadron Collider debates. The line between responsible popularization and sensationalism is often thin. Media tends to amplify the most extreme, catastrophic interpretations because they make compelling headlines, sometimes at the expense of the nuanced, reassuring safety assessments from the scientific community. This cultural journey reveals something fundamental about us. We are a storytelling species, and we use narrative to grapple with forces beyond our control. The Strangelet is a perfect monster for the atomic and digital age, a threat that is microscopic, invisible, and total. It represents our anxiety about science outstripping wisdom, about unlocking powers we cannot put back in the box. By playing out these apocalyptic scenarios in fiction, we perform a kind of collective therapy, testing our fears in a safe space. The fact that these ideas now feel familiar, that they have roots in both nature and Netflix, shows how deeply science shapes our modern mythology. Our oldest stories were about gods and monsters. Our newest ones are about particles and probabilities, but they are still asking the same eternal questions about creation, destruction, and our fragile place in the grand scheme. Fear is a powerful story, but physics is a meticulous editor. The most persistent myth is that our experiments could accidentally end the world. We have to dismantle this idea piece by piece, starting with the fundamental scale of reality. A quark nugget or a strangelet is unimaginably small. Its cross-section, the effective area it presents for collisions, is subatomic. If one were to pass directly through your body at a normal cosmic speed, the chance of it striking even a single atom in your cells is astronomically low. It would slip through the vast empty spaces within your atoms like a ghost walking through a wall. You would feel nothing and no damage would occur. The sheer emptiness of matter from the atomic to the human scale makes such an event harmless. This same principle of scale defeats the planet-eating scenario. For a strangelet to convert normal matter, its strong nuclear force would need to make direct contact with an atomic nucleus. But a stable strangelet, if it exists, is likely electrically neutral or surrounded by that protective electron cloud. This electromagnetic shield keeps it at a distance, preventing that catastrophic touch. It behaves like a perfectly smooth, inert marble, not a sticky piece of cosmic glue. Now consider the natural particle accelerators that have operated since Earth formed. Cosmic rays, often protons or atomic nuclei from deep space, strike our atmosphere with energies millions of times greater than anything the Large Hadron Collider can produce. These are not gentle events. They create cascades of secondary particles, and their collisions are far more violent than anything we replicate underground. If such high-energy natural collisions could create stable, dangerous strangelets, our planet would have been converted to strange matter eons ago. The fact that we and the Moon and every other rocky body we observe are still made of normal atoms is the universe's own safety report. It is a continuous billion-year experiment that has never produced a doomsday result. This leads to a critical tool for navigating sensational headlines, understanding the hierarchy of scientific ideas. At the top are established theories backed by vast evidence like general relativity or the standard model of particle physics. Then come robust hypotheses like the existence of strange quark matter, which are mathematically sound, consistent with known laws, and actively being tested. These are the frontiers of science. Further down are speculative conjectures, intriguing what-if scenarios that are physically possible but lack any observational support. At the very bottom lies pure fantasy, ideas that violate known laws or ignore basic constraints. The LHC Destroys Earth story conflates a robust hypothesis with a fantasy scenario, skipping all the crucial steps in between. It takes a real scientific concept, strips away the careful caveats about stability, critical size, and natural evidence, and replaces it with a dramatic, simplified ending. When you next see a headline about a planet-killing particle, pause and ask a few detectives' questions. Does the claim respect the scale of nature? Does it acknowledge the constant, more powerful experiments the cosmos is already running? And most importantly, does it distinguish between a fascinating theoretical possibility and an imminent existential threat? Real science thrives on uncertainty and testing. Sensationalism sells certainty and fear. By recognizing that difference, you move from being a consumer of scary stories to a participant in one of humanity's greatest adventures, the disciplined, awe-inspiring search for what is truly real. The search for the universe's true ground state is about to enter a new era of precision. Within the next 2 decades, a suite of revolutionary instruments will come online, each designed to listen to a different frequency of the cosmos's hidden song. Our particle colliders, the microscopes of fundamental physics, are preparing for profound upgrades. The high-luminosity Large Hadron Collider project will not increase energy, but will dramatically boost the number of collisions. Imagine turning a spotlight into a strobe light. This deluge of data will allow physicists to sift through the debris of countless mini-Big Bangs with unprecedented sensitivity, searching for even the most fleeting hint of exotic particle clusters that could be precursors to strange matter. Beyond that, concepts for future colliders, like the Future Circular Collider, aim to reach energies several times greater than today's machines, pushing deeper into the conditions of the primordial plasma. These are not just bigger machines, they are finer sieves designed to catch whispers we currently miss. While colliders probe the tiny and transient, new eyes on the sky will scan for the massive and permanent. In the field of gravitational wave astronomy, the proposed Einstein telescope represents a quantum leap. Planned to be built deep underground in Europe, this next-generation observatory will be 10 times more sensitive than current detectors like LIGO and Virgo. It will hear the mergers of neutron stars or strange stars from the farthest reaches of the universe, capturing their chirps with crystal clarity. The subtle differences in those waveforms, the telltale signs of a star's stiffness and size, could finally provide the statistical proof needed to identify a population of quark stars. It would transform gravitational waves from a new sense into a diagnostic tool, allowing us to literally feel the difference between nuclear matter and quark matter. Simultaneously, the Cherenkov telescope array will open a new window on the high-energy sky. This next-generation observatory, spread across sites in Chile and the Canary Islands, will detect gamma rays with unparalleled resolution. It will study pulsars and stellar remnants in exquisite detail, measuring their gamma-ray spectra like a forensic scientist analyzes a fingerprint. A strange star's bare quark surface and unique magnetosphere should leave a distinct mark on this light. By comparing the theoretical fingerprints of neutron stars and strange stars against the Cherenkov array's pristine data, astronomers may finally match a name to the face of a mysterious object we've been observing for decades. The dream, of course, is a smoking gun. Imagine the headline: gravitational wave data from the Einstein telescope confirms two merging objects are too small and too stiff to be neutron stars. At the same moment, the Cherenkov telescope array reports that one of those objects, prior to merger, emitted a gamma-ray signature perfectly matching a strange star model. This multi-messenger convergence would be the definitive discovery. It would not be a hint or an anomaly, but a coherent story told through ripples in space-time and flashes of light. Such a moment would instantly rewrite textbooks. The confirmation that strange quark matter is the true ground state would be a paradigm shift as profound as realizing the Earth orbits the Sun. It would mean that the most stable, perfect matter in the cosmos is not the familiar stuff of our periodic table, but a simpler, denser substance we have only just begun to fathom. Every neutron star in the sky would become a candidate for transformation, and every ancient quark nugget drifting in the dark would become a fossil of ultimate reality. The hunt is no longer for a ghost, but for a signature we are now building the instruments to read. Mastering the universe's ultimate building material would redefine civilization itself. Imagine a future not where we simply discover strange matter, but where we learn to shape it. This leap from cosmic curiosity to practical technology is the grandest engineering challenge conceivable, one that would demand we control the very forces that forge stars. The first property that captures a futurist's imagination is superconductivity. In our world, superconductors are materials that carry electricity with zero resistance, but they require extreme cold, often near absolute zero. Some theories suggest that strange quark matter in its cold, dense state could be a natural superconductor at far higher temperatures, perhaps even at room temperature. A wire made from this material would not just be efficient, it would be perfect, transmitting power across continents without a single watt of loss. It could enable levitating trains, revolutionize medical imaging, and form the backbone of a global energy grid with no waste. The power locked within strange matter is even more staggering. Remember, a sugar cube-sized nugget contains the mass energy of a mountain. If we could find a safe, controlled way to release that energy not through annihilation, but perhaps through a slow, catalyzed decay, a single nugget could power a city for centuries. It would be the ultimate battery, a near-infinite energy source compact enough to hold in your hand, making fossil fuels and even nuclear fission seem like primitive campfires. For construction, its density and stability are both a promise and a puzzle. A structural beam made of this material, no thicker than a hair, could support skyscrapers that scrape the edge of space or span canyons in a single graceful arch. Spacecraft hulls fashioned from thin sheets of strange matter could shrug off micrometeoroids and radiation, enabling true interstellar travel. We could build habitats on the surfaces of neutron stars or within the turbulent atmospheres of gas giants, places where normal matter would be instantly crushed or vaporized. Yet every one of these dreams crashes against the monumental challenge of containment. How do you handle a substance with the density of a neutron star? Its gravitational pull alone for any nugget larger than dust would be intense. A marble-sized piece would exert enough gravity to pull tools and even people toward it with alarming force. You could not place it on a table. It would fall through the floor, through the planet, seeking the core. To manipulate it, you would need force fields or some form of magnetic levitation exploiting its slight charge, holding it in a perfect, frictionless embrace within a vacuum chamber. The act of cutting or shaping it seems impossible with any tool made of normal matter. You might need to use beams of other exotic particles or precisely controlled gravitational waves, a technology far beyond our grasp. And the ultimate question remains, where would we get it? We cannot create it in any meaningful quantity with our current or foreseeable technology. The only plausible source would be to mine it from the cosmos, perhaps by sending robotic probes to scour the debris fields around ancient stellar collisions or to delicately harvest fragments from the crusts of strange stars. This would be an industry on a galactic scale, an endeavor requiring millennia of advancement. So while the applications spark the imagination, the path to them is a humbling reminder of our place in the universe's timeline. We are not yet star forgers, but by daring to envision that future, we chart a course for the very long-term ambition of our species. It asks us what kind of civilization we hope to become, one that can not only understand the deepest secrets of matter, but gently hold a piece of a star's heart in its hands. Our journey began with a hole punched through the galaxy and ends with a question about our own cosmic address. The existence of stable, strange matter would rewrite the fundamental nature of reality. It would mean the universe is not built upon the familiar architecture of atoms, but on a deeper, denser foundation we have yet to fully touch. The periodic table would become a temporary scaffold, and the iron in our blood a fragile, higher energy state. This realization carries a profound implication. If quark nuggets drift in abundance, then the cosmos is seeded with invisible, indestructible shrapnel from its most violent births and collisions. We live in a galactic shooting gallery where silent bullets forged in stellar mergers and primordial fires crisscross the darkness. Our survival is not a given, but a statistical gift, a testament to the vast emptiness that separates these cosmic bullets from our fragile world. It paints a universe of hidden, permanent relics, a cosmos where the most stable things are not stars or planets, but microscopic fragments of a deeper truth. Yet, if decades of searching ultimately conclude that stable, strange matter does not exist, the answer is equally profound. It would mean the atomic matter we are made of, the protons, neutrons, and electrons that form everything from DNA to distant nebulae, is, after all, the universe's preferred and most stable configuration. The iron nucleus would retain its crown. We would not be living in a metastable illusion, but on the solid ground of cosmic permanence. Our kind of matter would be the true, final product of stellar alchemy, not a runner-up. This outcome reinforces a special connection between us and the cosmos. We are not made of exotic stuff, but of the universe's most refined and enduring essence. The silence of the detectors would speak volumes, telling us that the abyss, while vast and violent, is not filled with phantom bullets of a different reality. Regardless of which answer emerges, the pursuit itself is the victory. For centuries, we have looked to the stars and told stories about gods and monsters. Now we tell stories about quarks and critical baryon numbers, about gravitational wave chirps and gamma-ray fingerprints. This shift is monumental. We are using the rigorous language of mathematics and the patient gathering of light to test our most daring myths against the fabric of reality itself. The hunt for strange matter is not just a physics experiment. It is a measure of our maturity as a species, our ability to replace fear with curiosity and speculation with evidence. It demands a humility that is both crushing and exhilarating. We are confronted with forces that can shatter space-time and states of matter that defy all earthly intuition. In that confrontation, we learn the limits of our intuition and the boundless potential of our reason. So, what does it mean for our place in the universe? It means we are the part of the cosmos that has awoken and begun to ask these questions. We are the temporary arrangement of atoms that has developed the ability to wonder if it is temporary. Whether we find that we are built on the universe's bedrock or perched on a precarious ledge, the act of looking changes us. It expands the realm of the known and maps the borders of the unknown. It reminds us that we are small, yes, but we are not blind. We are witnesses to a story of unimaginable scale and complexity, and we are slowly, painstakingly learning how to read it. The true ground state of the universe may be quark matter, or it may be the atoms in your hand. But the ground state of the human spirit, it seems, is a restless, beautiful need to know. From the quantum flutter of a strange quark to the silent tremor of a planet struck by a cosmic bullet, we have traced the edges of reality's strangest possibilities. We have journeyed from the heart of a dying star to the first moments of the Big Bang, hunting for a substance more stable than anything we know. Let us hold the three ideas side by side one final time. A quark nugget is a relic, a fossilized droplet of strange quark matter forged in the primordial fire or a stellar collision, drifting silently for eons. A strangelet is that same exotic matter, often imagined as a microscopic seed with the terrifying potential to convert all it touches, a potential ruled out by both nature and our most powerful experiments. And a relativistic cosmic bullet is either of these objects weaponized by pure velocity, a speck of mass turned into a planet killer by the simple, unforgiving physics of motion at light speed. This entire field lies in a breathtaking space. It is curiosity-driven science at its purest, probing questions about the fundamental state of the universe with no immediate application. It is a rigorous form of existential risk assessment, forcing us to calmly evaluate whether the cosmos itself harbors natural doomsday devices. And it is the engine of futuristic imagination, inspiring stories and technologies that stretch our vision of what a civilization could one day become. This intersection is where wonder meets wisdom. It reminds us that to understand the greatest dangers, we must first dare to imagine them, and to imagine the most glorious futures, we must first ground them in the laws of physics. Your curiosity is the fuel for this entire endeavor. It is the public wonder that supports the telescopes and the particle colliders, that reads the books and watches the documentaries. So keep asking the big, mind-bending questions. Support the scientific exploration that seeks answers, not with fear, but with patient, evidence-based awe. And tell us below which concept captured your imagination the most, the silent quark nugget, the phantom strangelet, or the ultimate cosmic bullet. The conversation about what lies at the foundation of everything is just beginning.